So, welcome everyone. EV charging is tricky, especially in Germany. Cars can behave differently, users might also not know what to do, and chargers can have bad internet connection, so they just take longer to respond. At JUCR, we tried to make charging less tricky by building everything in-house, from the charging station hardware to the consumer applications, so we create the best possible charging experience. Right now, we are the fastest growing provider for EV charging in Germany. On the left side, you can see a charging session in our app, which waits for the confirmation of the charger that it started successfully. It says connecting. So you don't really know what's happening. What does it mean? Is everything all right? Can I leave the car? Did it already start charging? On the right side, you see an ongoing charging session. And as a customer, you can now leave your car and you know everything is fine. And is that what we want to create at JUCR? So for us, we know that we need to assure the customer that everything is all right. And even if something is not all right, we want to assist in order to make it work. And this in the fastest way possible. And also while charging, the customer wants to know what's going on. So we also need live data and statistics. And finally, you want to interact with the customer, with the application and the charger in real time to, again, create the best possible charging experience. The session is about achieving a real-time behavior in applications with GraphQL and Apollo Federation. We are doing that on scale, in a distributed architecture, built on around 50 microservices and 20 federated subgraphs. With all of those services talking asynchronously via Kafka at around 1,000 events per second. So there's a lot of traffic going through, so you need to be really efficient. All the engineers here might agree that sounds like a lot of pitfalls. But today we'll walk through our entire implementation with all the ups and downs. So one way to achieve real-time behavior in applications is by polling. What you do repeated HTTP requests in regular intervals, let's say every 10 seconds. This also means that the minimum lag from having new information to the customer receiving that information is 10 seconds. In 5 minutes, your app will do 30 requests. But it's simple to implement, and because of that, it's even in most cases the better solution. Even though waiting 10 seconds outside in the rain, looking on your phone, feels like an eternity. And even worse, when you can have an immediate response. We will come to that later. Also, a big pillar of GraphQL is about efficiency. And doing 30 requests for 2 updates sounds like overkill for us. So let's see it in action. On the left side, we do polling every 7 seconds. This was our application before. While on the right side, we can already leave the car charging. For the customer, this feels way better. And the same basically goes also for stopping. So it immediately responds when you remove the cable. So we now want to have the right experience compared to the left experience. Then you need to use subscriptions. Subscriptions are basically a low latency pub/sub channel between the client and the server. In our case, between the Apollo router and our mobile applications. The cool thing is everything is built into GraphQL and also everything is built into Apollo Federation. So the whole implementation is super straightforward. Usually it requires some engineering effort. For us, it was worth it. How can we build this? So on the left side, we see the query our charging app is actually sending to our backend. It subscribes to new charging session updates. We basically want to know, We basically want to know if the charging session is still running. We want to know if everything is all right. We also want to get data from other subgraphs. So for example, the status of our charging station. We want to know what was happening in terms of a timeline. We also want to know, for example, how full is the battery or how fast is the car charging currently. For this, we use Apollo Federation. So the router is splitting the query into multiple parts, forwards this subscription to the subgraph owning it, while fetching all the other data from the other subgraphs. So the cool thing here, it's so deeply integrated that all the normal federation features you all know work out of the box here. But for this, the service owning the subscription needs to store all open subscriptions to a charging session. So if we model this whole thing, we would first think it's kind of simple. You would actually store a list of subscriptions next to your charging session. But on the right side there, you see a comment I would actually do in a pull request. Because subscriptions are infrastructure, and infrastructure has nothing to do with the domain layer. So what we need to do, we need to decouple the domain. When decoupling the domain now, so basically removing the subscriptions out of our model, we need to find something in between. We basically need to create a layer between the other services and our subgraphs. When there's now an update to the charging session, the service publishes the updates via Kafka to this new component. We will come to this. But when those updates are then done via Kafka, for example, it results in 0 code changes for us because our services anyways publishes those updates automatically to, for example, our billing engine. So we need to find something which you can hook in, which subscribes to Kafka, and then basically feeds the router with new data. It also needs to handle everything. It needs to know who has subscribed to what. And when a new event is coming in, it needs to know, should I drop the event or should I send a new request to the router, notifying it about an update. This is why we built a tool called Pathfinder. It's basically an event-driven relay between async message brokers, for example, Kafka, but you can also hook in like RabbitMQ or anything else, and the Apollo router. It's also highly configurable. So you have a single YAML configuration file. It supports multiple different SERDI formats, message brokers, different key value stores like Redis, and even an external schema registry. And also it can handle millions of incoming messages per second. So for us, it was the most scalable solution to build this. When you go back to our original architecture, we can see that not so much was changed actually, but the charging service is only publishing those updates directly via Kafka to Pathfinder. Pathfinder already subscribed to it, and we have now decoupled this whole handling of subscriptions from our service. So this is for us way more scalable because you don't need to implement the handling of those subscriptions into all of your subgraphs. For example, we started only making the charging sessions live. If you also want to make your transactions live, if you want to make charging stations live and basically give the customer the best possible experience, you can now just select multiple subscriptions, hook it up to different Kafka topics, and then feed those subscriptions directly from those Kafka topics. So for a platform, it's super easy to expose real-time capabilities if you already use Apollo Federation, in our case, the enterprise plan, plus an asynchronous message broker like Kafka. The first step when starting a subscription is basically the initialization phase. And that gets a bit tricky here. So the client is actually subscribing to the router. This is the normal flow. The router now is not subscribing at the charging service. The router now subscribes at Pathfinder directly. Pathfinder quickly validates the subscription with the router. And when everything is valid, it also makes sure that it can receive updates. When it can receive updates and everything is all right, we would insert the subscription into a key value store, in our case Redis. And after this is inserted, we are confirming the subscription at the router. So afterwards, our client can now receive live updates, our channel is established, and we can then move on to the main loop. What we can see here is that the control flow is basically inverted. So when you remember the polling, you would basically send repeated requests to the backend asking for new data. Now we can send on-demand updates from the charging service to our mobile clients without writing a single line of new code, basically. So when a new charging session is updated, the charging service, in our case, would publish those updates via Kafka. Pathfinder receives those updates, can transform the data, it knows which field to extract out of the event. It quickly checks if the subscription is still valid, because you can also define how long a subscription should be valid in the maximum time. So for example, for charging sessions, it's longer. But for other applications, it might be only 5 or 10 minutes. And you don't want to store data longer than you actually need. When the data is verified, Pathfinder will now send the updates directly to the router. So it extracts all of the data out of your message, serializes it, and sends it directly to the router. And now our client has the session updated in form of a multi-part chunk. So there are actually two ways of achieving this. This is once via WebSockets, and the other via the HTTP callback protocol. This is like quite newly launched from Apollo. We are focusing right now only on this HTTP callback protocol. The cool thing here is this whole process now takes milliseconds from the initial publish at the charging service, instead of having a minimum lag of, for example, 5 or 10 seconds to the customer. This doesn't sound much, but if it's really outside in the rain, minus 10 degrees in cold Germany, this is way better to have 100 milliseconds instead of 10 seconds, trust me. But for the termination, it's also kind of similar. So we have the same actors here. We can actually configure a Kafka topic as a terminating topic. So for us, we have a topic called charging session stopped. When a charging session is stopped, we also want to terminate all open connections which are done from the clients to the router. So that means terminating all subscriptions directly. When Pathfinder now receives this update, it can check if the topic, which was configured before, is actually a terminating topic. When it is a terminating topic, it will delete all open subscriptions, so you can even have more than one subscription per entity. It will delete all of those open subscriptions directly from Redis, and afterwards sends a message called complete to the router. This is like basically in the HTTP callback protocol defined, and when the router receives the subscription, the router will terminate all open subscriptions and will also notify the client that the data stream now ended. So we also don't need to make those subscriptions open longer than actually needed. The cool thing also is Pathfinder is built in a Kubernetes native way. So you have a declarative configuration of new listeners. You can support multiple 30 formats, like protobuf, JSON, JSON schema, or even an external schema registry, and everything is built inside. You can also rate limit the amount of updates sent from the router for a given topic. So if you have topics with a super high throughput, you don't want to overload your clients when nothing really changed. You can also just configure this in a YAML file and hook it up to certain topics, so you can configure everything on a per topic basis. The good thing also is its whole thing is deployable as a Helm chart, and you can decide if you want to deploy multiple bigger instances. So you can also hook in like 20 subscriptions with like 50 topics, for example. Or you can also run it in smaller, independently configured instances. So you can even run it, for example, as a sidecar. This works in the same way because Pathfinder parallelizes everything while still preserving the order of messages on a per topic basis. So even if you parallelize all the handling of the messages, you would never lose the delivery guarantees you get from your message broker. To make Pathfinder as scalable as possible, and this was for us a quite huge point when we implemented it, it needs also to be super efficient. So for this, we thought it's not really needed to use any third-party GraphQL server. We've just built a tiny part of required functionality ourselves in Rust, and also use the official Apollo parser for the AST. So using these mechanisms, we can, out of a previously inferred schema, we can auto-generate a GraphQL schema for your given subgraph. Pathfinder can update the schema directly at GraphOS and sync it all the time with your online schema registry, what you already know at GraphOS. So it basically acts like a normal subgraph you would deploy in any other way as well. It's also now open source, basically since today. So if everyone is interested in looking into it, it's basically in our GitHub. And what we learned from that is also the subscriptions are not a silver bullet. So for us, for example, it was a perfect solution to create super fast responses and basically real-time updates to our customers. But you really need to decide if you need it or not, because it still requires some effort, it requires infrastructure to build, and all of those things. But if you decide it's worth it, use the new HTTP callback protocol from Apollo. This makes things, on the one hand, way easier, and it makes it also way more straightforward to enable this whole thing in a fully event-driven architecture. Another thing is you shouldn't try to squeeze everything in a single service. This is the first mistake we actually did. We tried to put everything in one service, and then for us we saw, okay, it's growing and growing. If you now want to enable another service with those subscriptions, you would either build an internal library, you would somehow share the code, or most developers would maybe just duplicate the code and write a ticket for deduplication later. You should also align between mobile clients, backend, and infrastructure. Subscriptions are still somewhat complicated, but there are a lot of ways to do it in a really straightforward way. But regardless how you implement your subscriptions in a GraphQL environment, you need to make sure that everyone is aligned. So you need to align between mobile clients, mobile engineers, backend people, infrastructure people, and even product people, regardless how you implement it. Thank you so much.